everybody. Thank you for joining today's session of the Synthetic Intelligence Forum Online. It's my pleasure to welcome Julius, who is joining us from MIT. He's a PhD student in the computer science faculty, and his research is very interesting, very broad-ranging and eclectic, but particularly he looks at topics that have to do with responsible AI, privacy, interpretability, ethics of AI, things of that nature. So really, really interesting research scope. We know it's very relevant in today's day and age. So very happy to have Julius join us today. I'm going to welcome Julius to the screen now. Julius, it's a pleasure to meet you.
Nice to meet you as well. Thank you.
Thank you, Julius. And I see that your slides are shared, so I'm going to remove myself from the screen and then we'll transition over to you. The floor is yours. Thank you.
Great. So this talk will be, thanks for inviting me to give this talk, and I'm happy for the talk to be interactive. So if you have questions, please let me know while I'm going through. Most of this will be like an overview tour, because this area of interpretable machine learning is actually quite broad. There are different domains like NLP, which you will hear about next week. But here we'll mostly look at vision. So looking at images, models trained on images, things like this. And the idea will be to sort of give you a taste of the different kinds of challenges that are sort of happening in this area. So to sort of basically dive in, I'm sure it's no longer news to anyone on this call that machine learning and models based on machine learning are getting applied in almost any domain you look at: text, vision. Here I sort of put two examples. One is where is a radiology example where there the clinicians gathered radiographs. So what you're looking at on the left with A is sort of hip radiographs, and then you can train a model on this to predict whether somebody has hip fracture or not. And then medical records, so patient records have also been trained using a lot of different models as well. And so you can see that these kinds of tasks are usually very sort of high stakes. It's important that the model should be accurate, and it's also important that the model is learning the right thing. You can also apply these kind of models to molecular synthesis. So here the idea is that you want to sort of augment what an organic chemist will do. And here you're supposed to sort of train a model to predict different properties of to actually synthesize a particular molecule. In some other case, you might actually predict whether the molecule is toxic or whether the molecule has certain different properties. So the general idea is that more and more, a lot of machine learning models are being applied or sort of injected into domains where things might necessarily be done by hand or by a human. And there you need to be able to sort of understand what the model has learned to beyond sort of looking at accuracy. So those are some of the motivation for why there's sort of increased emphasis on interpretability. And so the big issue that happens when you train a machine learning model, especially one that has a lot of parameters where it's not necessarily clear what the model is doing a priori after you've trained it. And so the big problem that happens is you could train a model and get a test set accuracy, but that necessarily might not tell you what the model has learned. So in this case, I'm just showing a very typical example these days in radiology where you have skeletal radiographs. So the skeletal radiograph you're looking at on the left is bone x-rays. And here, this is one of the tasks that radiologists do where like patients will come in, they'll take an x-ray of the hand. And the idea here is they often have very different tasks they like to do. So one would be to predict the age group from the bone x-ray. So here, the radiograph will be fed into a model. The goal of the model is to predict if the person is a toddler, an adult, or a teen. And here you can train a neural network model on this, the convolutional neural network model. And this model might get 97% accuracy on a test set, which are images that the model did not see while you were training it. And so if you look at this number, just 97%, is it straightforward to be able to go from this accuracy number to say, yes, this model is good enough that a radiologist should be using it, or instead of having a radiologist do this task, we should just have the model do this task. And so the challenge there is it's not clear just from the test set accuracy what the model has learned. If the model has learned the right associations, if the model is relying on clinically relevant variables. And so there's a lot more that you need to do to actually audit the model to make sure that the model is relying on the right things. And so this challenge is usually one challenge that motivates the need for sort of trying to interpret your model or dive into your model or gain insights about the model. And so it's the idea of sort of moving beyond accuracy. If I have an accuracy number, it doesn't tell me whether my model is reliable or not. I just know that on the test set that I gathered, the model is performing well. And the reason why you should care beyond accuracy is that, so this is an example I'm putting here, and this paper was published last year by a bunch of clinicians at NYU, I think. And what they did was they trained sort of an inception model. If you're familiar with the deep learning literature, they trained an inception, I think V3 model. They trained it on hip fracture radiographs. So the goal of the model was to take in a radiograph and then decide whether or not the person whose radiograph it was has hip fracture or not. This is a task that a radiology would normally do. And one of the things they found was they were able to train a model that was very accurate, but then the model was essentially relying on the scanner of the machine that was used to take the radiograph. And here, one intuition might be that, so this is not necessarily the reason, but one intuition might be that, let's say you come in and you take a standard radiograph. If there's something wrong with you, they might decide, I'm going to take this patient and have them take a radiograph from a different machine. And so what would happen there is that you would have a case where all the people with hip fracture are taking radiographs from a particular machine, and all the people that don't have hip fracture have radiographs taken on one machine. So if you train a model on this, it might just sort of rely on the frequency patterns of a machine and then it not necessarily actually detect whether somebody has a hip fracture or not. So this was one case where the model was relying on the scanner model to predict whether or not the patient has hip fracture, which is not what you want a model to rely on. Another one is, this is from a data set called Pascal VOC. So computer vision, this is a data set that is very popular in the computer vision community. And the idea there is sort of classification. So here, this is the horse category. And this is from a paper by Lapushkin et al., also from last year. And what they were doing was, here they have a method that sort of highlights what part of the inputs, so what part of the image the model was relying on to make its decision. And if you see on the top, you see the image of a horse, and then you see the marker, essentially, which is sort of the copyright info of the person that took the picture and the website. And so what you would see for this specific model that they were sort of interrogating, what they found was that the model was relying on the marker. So all the horse images in the data set had this marker. And so essentially the model was relying on that marker to figure out which images and the inputs in the training data set were horses, instead of actually relying on the horse subject. Another big issue that you tend to find in a lot of models, if you're not careful, is that the model would rely on the background instead of the actual object that you're trying to classify. So imagine if you're trying to classify between two groups of animals, let's say cats and dogs, and then you have all the dogs that are outside on the green grass, and then you have all the cats that are inside on a sofa or something. If you gather this data set, the model could just rely on green grass and sofa to decide whether or not an image is a cat or a dog. And so this is an example of a spurious correlation. And the reason why this is an important issue is because if you only look at the test set accuracy of your model, it's not very easy for you to tell just from the tested accuracy that your model is only relying on the caption. You need another tool. You need some other way for you to sort of dive into your data set, dive into your model, figure out what your model is relying on. And this is sort of the motivation for interpretability. And so to sort of summarize the things that I've just said, the reasons why you need interpretability is that a lot of the time you're about to deploy a model, or you've deployed a model and you're trying to figure out what kinds of mistakes is the model making, why is it making some particular kind of mistakes as opposed to the other ones. That's one reason why you usually need interpretability. Another one is you might want to sort of gain the trust of end users. So one popular one that people always talk about is that, let's say you are buying something online and you're looking at a recommendation system. So let's say you're buying books on Amazon and a book was recommended to you. You might want to know why the book was recommended to you. Or, for example, Netflix does this sometimes where you might be watching different movies and there might be a row in your Netflix pane that says something like, because you watched this movie, that's why we're recommending all of these other movies to you. So sometimes you might want to sort of show your end users things like that to sort of explain why they're seeing a particular model behavior. Another one that is sort of starting to emerge is the idea of legislation actually requiring some form of explanation. So in GDPR, it's still there's something called the right to explanation, though it's unclear if the right to explanation as written in the GDPR actually requires you to have model explanations. But what the right to explanation is trying to get at in GDPR is this idea of if a model is making a decision about a person. So let's say you have a model that is determining your credit score or determining whether or not you get a loan. One thing you might require is that the model should give you an explanation about how the decision was made. So in the US, for example, if you apply for a credit card and you're denied, you get a letter in the mail that says something like, you've applied for too many credit cards in the past or something like this. So you get some reasons why you were denied. And this idea is to sort of take that idea of the reason why you were denied into model behavior as well. So a lot of this is coming at it from different angles. So because of a lot of these different interactions, the field of interpretations and machine learning has sort of gained more mainstream attention. And so to sort of demonstrate things more clearly, a lot of my focus for focusing on explanations and interpretability is usually trying to understand how you can debug a model. So here I'm showing sort of a prototype example. So here you have a model where you train it on images of animals. And here you feed in this animal and it's sort of predicting that the animal is a husky. And then you might ask, so why is the model predicting that the animal is a husky? And here, what this explanation is showing is it's showing you what parts of the image the model most relied on to make the decision that the input was a husky. So you might have seen, if you're very familiar with this literature, you might have seen these kinds of explanations before. But this is sort of like a feature importance of the different dimensions of the inputs. And if you notice, the model is mostly highlighting the snow. So the image, there's a snow in the background, and a lot of the images of the huskies in this data set are actually they have a snow background. This was sort of constructed to be the case for this example. And so one thing you might be interested in is to say, oh, I have an image. I see that the model is actually relying on the background instead of relying on the actual object itself. So what I should do is now I should go back and fix my model, maybe gather some examples of huskies that are not on snow backgrounds, or do something else, maybe retweak my model in a way that it's not relying on the background or the snow here, but it's relying on the actual object. And this is sort of the motivating example, at least from my perspective, why I've sort of focused on this work. And the idea is to sort of better do interactive debugging or more sort of principled debugging of large-scale models. So to take so far I've sort of given you some kind of motivation and to sort of explain why this field has sort of gained more attention. And one thing that sort of you would see if you start to dive into this literature more is that there are different names for what the things that I've described. And some of those names are like interpretability, explainability, transparency, maybe more broadly, intelligibility. And so these terms, while they are not the same and there are different sort of connotations that are attached to each term, they're getting at the idea of looking beyond the accuracy or looking beyond sort of numeric metrics into trying to like diagnose the associations that models typically learn. And so depending on who you talk to in this area, they're either working on interpretability or explainability or transparency or intelligibility. But I'm sort of grouping it together here to sort of put it as an umbrella term in some sense. Though if you actually dig into the details of this, they actually mean slightly different things. But the broad goals of this terms is the idea of sort of getting more introspective about what the models that we build actually learned. And so I'm going to use the term from now, I'm going to use the term explanations. Even though the way I'm using explanations is as a catch-all term that sort of relies on all the other terms that I mentioned in the past slide, but depending on the literature you read, explanations might actually mean different things. And so so what does it mean to sort of explain a model? And here, the sort of take I'm going to sort of push forward in this talk is that explanations are artifacts or sort of things you can get from a model that give you insights into what the model is relying on to make its final output decision. And so one good definition that I really like is from this, there's a classic paper by Doshi, Velez, and Kim in this area. And the paper sort of says to interpret means to explain or to present in understandable terms to a human. And so what that means is you have two components. You have a model and you have a human or a person trying to sort of get insight into the model. And a lot of what interpretability and explainability involves is sort of extracting insights from the model and having it sort of convince an end user, a human, of what the model is sort of relying on. And so while this is somewhat high level and a vague definition, one way you can operationalize this is that this kind of thing, you can operationalize it in two ways. One is you can say, if an end user is better able to simulate a model, then they understand what the model is doing. Another one is if an end user is able to fix a broken implementation of a model, then they understand what the model is doing. And this idea of debugging, so to give you an example, here's what it means. It could mean that, let's say I have a radio and the radio is broken and I give you the radio and say, fix the radio. If you're able to fix the radio and return to me a radio that actually functions perfectly, then this is evidence that you might understand how the radio functions, all of its components, and you're able to sort of rewire the radio and fix all of the issues that might be wrong with it. So these are two ways you can operationalize these definitions, even though the definition that I've talked about here can be somewhat high level. So like I mentioned, the field of interpretability and neural networks especially is sort of on a big rise. And this graph is actually from mid 2019, so I should update this. But the general idea is that there's a lot of work that is coming out of this area because more people have sort of recognized the idea of we need to sort of understand what those models are relying on, especially if you have spurious correlations. So the rest of this talk will mostly be focused on post-hoc explanations, and I will say what those are in a minute. But there are other kinds of explanations, and there are other ways you can explain your model. So in this area, roughly, I would say there are two paradigms for how you should go about sort of explaining or interpreting models. The first paradigm is what I've sort of termed interpretable models. These are models that are just the way you design the model is interpretable to a human from scratch. And I'll tell you what that is. Examples of that are sort of rule list. If the rule list is short, it could be sort of interpretable to a human. Penalized regressions are some forms of penalized regressions have this property. Additive models also, some forms of additive models also have this. And this is actually different than, imagine you have a data set and you train, let's say, the biggest neural network model you can on this data set. And then you come in post hoc and say, now I'm going to try and explain what this model is doing. So these are two different paradigms to try and achieve interpretability. And in the literature right now, it's still not clear if one is more reliable than the other one, or if one should be done almost exclusively. But there are different sort of camps and different ways you can go about sort of achieving this. I will mostly in this talk focus on post-hoc explanations, but I wanted to bring up that fact just so that if you're interested in this literature and you want to dive into it after this talk, to also keep in mind that there are different ways to do this kind of interpretations. So to give you an example of what an interpretable model would be. So here is what is typically called a rule list. And you can think of this as somewhat like a one-sided decision tree. And here I'm showing this example from this paper by Wang et al. From 2015. And what they've done is they've trained this model on a mammographic data set. And so this is a data set that predicts whether or not so it predicts the risk level of the actual inputs. So so you can think of it. So think of it roughly as sort of whether it's saying breast cancer or no breast cancer, even though the actual task is a little more fine-grained than that. But you can think of it as the model is trying to predict whether somebody has breast cancer or not. And so what this model does is it's basically as it's written here. So if the input has irregular shape and the age of the sample is greater than 60, then the probability of, let's say, breast cancer or malignancy risk in this case is 85%. And so this is the entire model. And you can think of this as a decision tree. So for you to interpret a model like this is essentially straightforward, because let's say you have a new input, you basically just take the characteristics of the input, you say, all right, for this input, I'm just going to walk through this rule list. Does the input have a regular shape? Is the patient age above 60? If yes, then I know that the probability is 85.2%. And I know that the reasons why the model is predicting 85.2% is because of the irregular shape and because the age of the patient is above 60. And so that's what I mean when I say the model is interpretable from scratch, is that you're designing a model where it's essentially sort of more constrained to be interpretable because you're relying on these features that are human interpretable. So this will be a rule list. So like I mentioned, there's actually a big debate about whether you should do post-hoc explanations or design interpretable models from scratch. And I think if people are interested, I can talk about this at the end of during the question and answer phase. But here, this is a paper by a professor from Duke, Cynthia Rudin, who, so she's actually a pioneer in this field, and she's done a lot of very interesting work in this area. And in her, in this paper, her opinion was that you should design models that are interpretable from scratch, and you should not interpret them post-hoc. And so, and she makes a lot of very interesting points. And if you're very interested in this area, I will actually encourage you to read this paper. It's very fascinating. But having said that, everything now that I'm going to talk about will be post-hoc explanations. So now we'll sort of just, the rest of this talk will mostly survey different kinds of post-hoc explanations. And the different properties they have and how you might use them at different points. And then we'll end with the challenges. So what are the problems of actually using these different methods? And by design, I've sort of made this part not necessarily deep. So at the end of this part, you might not necessarily know how to actually come up with these explanations, but you will sort of understand that these explanations exist, and they're actually open source tools that implement a lot of these different ideas. And so it's very easy to sort of get hold of them. But I think it's important to sort of survey what's going on in this area. So the first kind that I'm describing here, I've sort of called it examples or prototype method. And these are methods that they use examples to explain what a model is doing. So let's say here we have a cat and a dog data set, and we train one of these convolutional neural network models on this data set. And it tells us that the inputs on the left, that it's a dog. We might then say, okay, so why is the model a dog? And one form of answer to this question of why, even though the question is somewhat ill-posed, but one form of answer to this question could be, what are the training points that the model most relied on to influence its decision of the prediction of being a dog? And here, what the model can surface. So this is an example where we have a test point, the model predicted it's a dog, and then in order to make that prediction, the training points that the model actually looked at are these different examples here. And so here, this is one way of explaining, where you would say, I'm going to show you similar items that the model saw in training that it relied on to actually give you its prediction. This is something equivalent of, like, let's say I train a model to predict whether or not I should give you a loan. And then I decide, oh, I'm not giving this person a loan. One form of explanation can be, oh, in my training set, there were 3 people that were similar to you, that had your similar characteristics, and all of them defaulted on the loan that I gave them. So I decided not to give you a loan because these 3 people defaulted on the loan. So that's what this explanation is trying to convey. So these are sort of, you can think of this as sort of, they use examples to explain what the output of the model is doing. Another one is what it's called a sensitivity map. You can ignore the equations on this. I sort of copy pasted the slide. The equations are not necessarily that important. So here's a task where the model is predicting, it's doing object detection. So in the image on the left, the lady is eating a corn. She has a corn orb sort of held against her face, and she's eating that. And the model has correctly predicted that it's corn. One thing you might now be interested in is, why did the model predict corn? What parts of the image did the model rely on to make the prediction corn? And this can lead you to generate another image where you highlight what parts of the image led the model to predict corn. Here is one form of that, which is called a gradient. And here, if you're sort of familiar with how gradients work, this is sort of telling you that which parts of the image will I change that will most change the output, the prediction of corn. And so these kinds of things get called either like saliency maps or attribution maps or sensitivity maps. The name for these things is actually somewhat flexible, but you can think of them as like, they're forms of heat maps that tell you where the model is relying on in your inputs. And they usually work on a single input basis. So if you have another input where another person is eating corn or is just a corn on a desk, then the visualization will change. And so this kind of visualizations are visualizations that you sort of have for single inputs in your sort of single inputs in your test examples or single inputs that you're interested in. And I've sort of included some code here. And the reason why I've included this code is that these methods are actually very popular. And one of the reasons why they're very popular is that they're very easy to implement. And so they're very easy to implement. And the reason why they're very easy to implement is because in deep learning and sort of machine learning these days, there are a lot of automatic differentiation tools, and these tools usually take gradients very easily. And so to actually get the image you're seeing in this the image that I'm showing you here, all you need to do is call, if you're familiar with TensorFlow or some other thing, you just call TF gradients or something.grad if it's another thing you're using. And the code that generated this image is actually open source, and you can use it if you want. So another one thing that I will show now is that these visualizations, there's essentially a cottage industry of visualizations, where the way this has been generated is with a gradient. You can do something else to also generate other kinds of visualizations. So here's another visualization that tells you where the model is relying on to make the prediction corn. And you can see, so the method here is called Smoothgrad, but just think of that as a name. The details for my explanation here don't necessarily matter. But what this method is doing is that you can see it's a little more localized than the previous gradient. So if I show it, so this is what the gradient looked like, and this is what Smoothgrad looks like. So you can see Smoothgrad seems to be highlighting where the corn is, and it's sort of more focused on. So the more red the portion of this image, the more the model is, the more relevant that part of the image is to the output. And so what this is saying is that, oh, the model is mostly relying on the corn and maybe a little bit of the facial structure of the person eating the corn. And so this kinds of visualizations have been developed very, very widely, and they have been used all over the place. So another one of these visualizations is called integrated gradients. And it's essentially you integrate the gradients from a baseline to an out to the original model. And so there are different ways of generating this visualization. So each one of the visualizations you're looking at here is essentially a different paper or a different way of interpreting the same model that generated corn. And so this is one way of interpreting these models. And usually what these are generally called, some people call them attribution methods. If a visualization method has a particular property, it's called an attribution method. But most of the time, you can sort of lump them under the moniker of heat maps. So there are heat maps that tell you where the model is focusing on in the input. And one thing that we'll get to is that even though a lot of these visualizations are quite visually appealing from a human endpoints, it can be very difficult to use them to debug a model or to use them to actually make actionable decisions about your model. And as we'll see, some of these methods actually have counterintuitive behavior when you start messing around with them. So this is one very popular way of interpreting models. And so I've always been showing you images. You can actually use the same methods on molecules. So at the beginning of this talk, I mentioned how a lot of machine learning is also applied to molecule design, molecule property prediction, toxicity prediction, things like this. And so here, this paper is using something called integrated gradients to visualize the importance of the different bonds in this molecule on the actual binding property of this molecule. And what you see here is some parts are red, some parts are blue. They sort of encode positive and negative attribution. So a lot of these methods, you can also apply them to text. You can apply them to images, to molecules, discrete objects, even though that's slightly more tricky. And they've been applied very widely. And so these are some of the things I'll talk about now. So one thing that one issue I wanted to sort of bring up here is that when you sort of Google interpretable machine learning or you look up papers on interpretable machine learning, you come across things that are, they seem very, very impressive on first sight. So if you sort of go back to this molecule example, you can see the the explanation is sort of highlighting which parts of which bonds are more sort of attributed for the output you're interested in. Or if you look at a lot of these visualizations, so let's say this one, for example, you can see that the visualization is mostly capturing where the corn is. And at first sight, you might think, okay, the problem is solved. We know how to interpret our models. Everything is good now, so let's just move on. But what I want to sort of talk about in this part, so this is sort of the challenges part of the talk, where there are actually a lot of big problems in this literature. One of them is about correctness. The second is about privacy, and the last one I'll talk about is about manipulation. So correctness, meaning it's unclear if the visualizations that have been generated from some of the interpretation methods are actually telling you what the model is relying on. And I'll talk more about this. Another one is privacy. The reason why privacy is important here is that from a lot of these explanations, you can actually you can recover the models, you can tell whether or not your input was used in the training set. The manipulation attacks talks about how a lot of these explanations can be very easily manipulated. So a model that predicts dog, you can make the explanation focus on the background or the dog or the corner. You could basically manipulate the explanation as much as you want without actually changing the output or drastically changing the model, which sort of tells you that a lot of work in this area still needs, there still needs to be more work in this area to actually, before the problems are solved. So these are the three challenges I'm going to end with, and then we'll sort of go into question and answer. So the first one is correctness. So here I'm giving you an example of a skeletal radiograph. So this is the skeletal radiograph that I talked about at the beginning of the talk. And to remind you what the task is, you take a skeletal radiograph, and the task is to predict the age of the patient whose radiograph was taken. And so this is what a model does. And remember, you can generate these heat maps that tells you where the model is looking at in each one of the different samples. So the black and white images on the bottom, the two black and white images on the bottom are two examples for the same image. And the image on the left is of a normal model. So let's say you train a model on skeletal radiographs, you predict the age of a skeletal radiograph, and then you compute something called guided backpropagation. You don't need to know what guided backpropagation is, but it's a method of computing a heat map. So if you compute guided backpropagation on a trained model that you got, the one on the right is if you compute guided backpropagation on that model, but then before you do that, you completely randomize, let's say, 50% of the weights in the model. So now the model is predicting garbage. And not only is the prediction garbage, the weights of the model are randomized. So the weights of the original model are what you got from training. The weights of the new model are what you got just from reinitializing the model or randomizing it. And you'll see that from these two images, the visualizations you get are actually almost identical. And so that means the visualization you get for a model that is doing random predictions is the same as the visualizations you're getting for a model that's actually predicting very well on a test set, which tells you that the visualization method is unable to distinguish between a model that is 100% accurate and a completely reinitialized model. And so this is a property of guided backpropagation. And this property has been found for several other methods as well. So this is one problem with a lot of these visualization methods, meaning sometimes the heat map doesn't change when you randomize the weights of the model. And here is another example, and you might not be able to see this well, but essentially you can take one of these big inception models and then reinitialize all the weights. And you start reinitializing the weights from the top layer all the way to the bottom layer. And for some methods like guided backpropagation, you'll see almost no difference as you reinitialize the weights until you get to the lower level weights. And so this is a big problem, because if you're trying to tell the difference between a model that is able to rely on spurious correlations from one that doesn't, then it means that a method like guided by propagation might not be able to tell you the difference between those two methods. The second thing I mentioned was manipulation attacks. And I should say that if you have more questions about the specifics of what I'm talking about, you can bring them up during the question and answer period. Because I'm sort of working towards the end here, so you'll be able to ask those questions very soon. And so what you can also do is manipulation attacks. So in this image that I've put here, this image is from a paper by Gorbani et al. From 2017, and the point of the paper is essentially you can make these heat maps, you can change these heat maps arbitrarily without actually changing the output of the model. So the first row in this image, so each column is different examples. So simple gradient, deep lift, and intergradient gradients are all three different methods of generating heat maps. Now, the first row, the original one, that's what the model, that's the heat map for the original model. So the second row is essentially what the paper did is you can manipulate the heat map to focus on a completely different part of the image. And to also, the prediction doesn't change, but the explanation has completely changed now, which means that you can manipulate a lot of this explanation. So one example of this that might be more topical is that, let's say you train a credit scoring model. And it so happens that your credit scoring model relies on something like the zip code of your, let's say this was a spurious correlation in a data set, and the credit scoring model you trained relied on your zip code to determine whether or not to give you a loan, to give you a loan, let's say loan scoring model. Now, what somebody can do maliciously is if they see that the explanations from their model is saying, oh, our model is relying on zip code to give loans, which is not necessarily something you might want to rely on. It's possible to manipulate this explanation and make it rely on, let's say, income, which is something you might want a loan scoring model to rely on. And so this is a property you can actually take advantage of in real life, and something you might not necessarily want somebody to take advantage of. So the upshot here, what you should take away from this is that a lot of heat map based methods can be easily manipulated, and it's still an open question of how to actually defend against this kind of attacks, and even though some works are starting to emerge that do this. Another big problem is privacy. So privacy in the sense of re-identification. So there's this quote that I really like. It's sort of around what's called the fundamental law of information recovery, which is that overly accurate answers to too many questions would destroy privacy in a spectacular way. So let's say you're a company that you're a startup, and your job is you train machine learning models on radiology images. And what you do is your customers, they give you a radiology image. Your job is you generate the model on those images. You generate very accurate model on those images. You predict, let's say, the age, and then you give them explanations. And so this might be one way your system functions. So you train predictive models, you get inputs, you give API calls that are able to answer outputs and explanations. So one big problem with this is that giving the outputs and the explanations is actually very problematic. So there's a lot of work, well, maybe not a lot of work, but there are a few different works that have shown that you can very easily reconstruct your model from either the explanation or the output. So imagine you're a startup and you train models on radiology data sets. If a hospital queries your model a few times and you give them explanations, you're essentially giving them your model. Because what happens is from the explanations, they can reconstruct the model that you built. And then how do you make money? How do you defend your business? How do you make money if all of your customers are reconstructing your models? How do you sort of build a defensible business? So this is actually something that's counterintuitive, which is that the more explanations you give from your model, the more likely it is that your model is going to be easily reconstructed. And so this is another challenge. Can you give explanations that still prevent the model from being reconstructed? Essentially, I think this question is still mostly open and is still being adequately addressed. And some of the people that have looked at this question of privacy and explanations are, so if you sort of Google maybe Tramer et al., membership inference attacks on explanations, this Mealy et al. Paper, they are the ones that sort of looked at a lot of this question. So now I'm going to essentially sort of conclude and try and take your questions. And the things you should take away from this presentation are that the field of interpretable machine learning is very exciting. There's a lot of work that is emerging. I've mostly talked about sort of the heat maps and visualization methods on image data sets. Some of this work is going on NLP, and I'm guessing Sebastian will actually talk about some of that next week. So there's a lot of work in NLP, in, let's say, speech or other different data modalities as well. But it's still an open question of if these interpretations are actually useful in practice. So one big challenge is that it seems that a lot of companies are not necessarily relying on this interpretation. Some companies are using them, some are not, but it's not clear how widespread they are actually in practice. And I'll be curious to hear if some of you work at companies where you use interpretations. The second thing that I talked about here is those challenges. So I talked about the challenge of privacy, which is if you release a lot of explanations about your model, it's very easy for your model to be reconstructed. A lot of explanations can be easily manipulated. Actually, almost every explanation method I know can be very easily manipulated. So especially even easier for deep neural networks. Assessing the correctness of explanations is very difficult, especially post-hoc methods. It's very difficult to know if the explanation is actually true to the model or the explanation is just reconstructing some kind of artifact. So these are challenges that are still ongoing, and a lot of work is actually focused right now on trying to do a lot of those things. But one last thing to mention before I guess opening up for questions is that there's a lot of work here that's been sort of developing open source tools. So if you are familiar with this with this line of work, you've probably heard of something called Lime, SHAP, and a lot of different methods. And usually in that case, what you are seeing more and more is that a lot of people are open sourcing packages and tools that you can use to interpret models that you train for yourself. And so I can mention some of those if you're also interested. But so that's the talk. I'm happy to take questions now.
Thank you very much, Julius. That was a very thoughtful and thought-provoking talk. So thank you for that. Before we go to questions, I was wondering if perhaps I could just request you. You made a very kind offer. Cynthia Rudin's paper, you mentioned that if we're interested, we'd like to maybe hear a quick summarization from you of her main assertions and arguments, and maybe your critical reflections. Because I mean, since that paper came out, you've had the opportunity to reflect on it. Do you agree with everything they say? Are there certain things which you feel you would slightly maybe look at differently? So just a quick summary of what they say, and perhaps even if other research has now superseded that and come later in time, and then your critical reflection. Thank you.
Yeah, that's a good point. So the essential thesis the paper sets forth is that especially in high stakes decisions like healthcare, maybe recidivism, so a lot of like predicting whether somebody is going to reoffend or not. A lot of these high stakes decisions, the paper makes the claim that you should not do post hoc explanation. You should not build a model and then go in and try and interpret it afterward. You should build a model that is interpretable from scratch, where you know essentially what the model is relying on to make its decision. And so that's the main sort of thrust of the paper. And the reason why they say this is that because it goes to some of the challenges you see with post hoc explanations, which is post hoc explanations. If you build a post hoc model, so these are some of the things she says in the paper. If you build a post hoc model, then now you have to decide whether or not your post hoc model is reliable. So you have to check whether the new thing you built is reliable, and you have to check whether or not it reflects what the complex model is doing. Another reason why she says is that one thing a lot of people talk about is this interpretability accuracy trade-off, that if you build a model that is interpretable from scratch, it will be less accurate than a black box model. So this is the idea of, if I want to predict somebody's credit score, I should just build a giant random forest model, gradient boosted tree, and then interpret that post hoc. Or I should build like a really small logistic regression model or something like this. Logistic regression model with small features. So she made a lot of these points, and I think it's still open whether or not she is completely correct. But I will say that a lot of the challenges we see with post hoc explanations, we don't necessarily see that with methods you design from scratch. So there are trade-offs. If you have to design a method to be interpretable from scratch, it seems slightly more difficult, maybe not slightly, it seems substantially more difficult than to build a giant discriminative model and then interpret it from by scratch. Because what you have to do to build an interpretable model is you have to constrain it somehow, maybe learn a rule list or constrain the features you use, or you have to like basically build constraints into your model. And when you're building constraints into your model, it means you most likely can't use a generic optimization method. You have to sort of be more clever about what you actually do, which is it's slightly more difficult than just taking all your data set, building a model on it, and then interpreting it after the fact. I will say, in terms of my own personal opinion, more and more I'm leaning towards her perspective of, if there's a way to sort of even bridge both worlds, where let's say you have no idea what the important features are in your model, you build some sort of giant black box model, and then you now start to sort of decompose the model to make it more interpretable so that you can like debug it more easily. I will say, in some of the things I've looked at, it's substantially, at least this is my opinion here, it's substantially easier to debug a model, to sort of play around with the model if it's interpretable from scratch, than it is to do it with post hoc methods. But this could be because post hoc methods are still somewhat a new phenomenon, and more work needs to be done to actually make sure that they are useful. But I will say, from my perspective, a lot of interpretable models that are interpretable from scratch are substantially easier to use to debug or predict what the model is doing than post hoc methods. But it's unclear if that's because post hoc methods are just, we haven't worked on them enough to actually make them as reliable as interpretable methods. And so I will say the evidence is in her direction, but it's not as strong. There's still, the field is still battling back and forth.
Okay, excellent. Thank you, Julius. Yeah. There's a couple of questions here, so let me put this one up. And so this question is asking about GPT-3. So, you know, when we talk about models with 175 billion parameters, I mean, there's many ways to look at this question. One way perhaps you can approach it is, you know, in the beginning of your talk, you talked about the fact that sometimes we use synonyms. We use interpretable, transparent, explainable.
Yeah.
What's very interesting is you also used a phrase, which I wanted to come back to. Maybe this question gives us that opportunity, is understandable. Because even if there was a way to, if you think, even from what you mentioned, Julius, even if we put aside the notion that the interpretations that are, or the explanations which are being outputted are technically correct. But then the question becomes that, you know, when we look at it from a human cognitive perspective, are they truly understandable? So when you have 175 billion parameters in a model, what kind of an explanation would even be understandable to a human? So I suppose, can you comment on these mega giant models that are now being released? And where is that link between what's interpretable technically and what's functionally understandable?
Yeah, so I think this is a very good point. Like, yeah, I've also I think when you have a lot of this massive, so there are two. This is why the interpretable versus post hoc methods, there's still this debate. So with a GPT-3 model, you have to sort of rely on methods that will probe it and try and see how it behaves on different examples. So for example, I'm sure you've also all seen a lot of those Twitter threads where they'll say, oh, I gave GPT-3 this and it's predicted this, I give it this, I predicted that. A lot of those are post hoc. It's difficult to know from those things whether or not GPT-3 is actually relying on them, or if it's what is the source of a lot of those behavior that we're noticing. And I will say essentially the problem is still completely wide open about how you interpret a model with that many parameters, because one of the things that happens with a lot of models with those parameters is that it's very easy to fool yourself in some sense. So if you gather, let's say, 10 or 15 examples, and you look at the behavior of GPT-3 on those 10 examples, you could easily conclude, oh, GPT-3 is behaving this way because it's able to like do this different things. But it could be that if you collect 20 or 30 other examples, it might be behaving completely differently. And so this is a problem where if you have massive amounts of parameters, you just have so many degrees of freedom to sort of fit anything and to describe any kind of behavior. And so there's a lot of work that is actually, especially in the NLP community. So there's something I didn't talk about at all in this presentation, which is the idea of probing. So a lot of people in the NLP community, what they do is, and not just NLP, but generally what they do is, let's say you want to figure out whether GPT-3 relies on some property of interest. You will collect a data set where you can measure that property, and then you measure the output. So you would sort of feed that data set through GPT-3, see what it predicts, and then you would train let's say, a linear model, a logistic regression model to see whether or not GPT-3 actually learned that behavior. So it could be that, oh, GPT-3 is able to easily negate a sentence, for example. So let's say if you give, I'm going to the mall, I am not going to the mall. So it could be that you want to figure out if GPT-3 is able to better, if it has learned negation. So what you do is collect a data set where you have a bunch of positive examples, negative examples, and then you feed those data sets through GPT-3, and then you then build another model to see if GPT-3 has actually been able to learn this kind of thing. So those methods are actually popular, but they also, in some ways, they suffer from some of the problems that post-hoc methods suffer from. And so I will say that the idea of interpreting GPT-3 or models that have like multiple like interactive components, this kind of thing is still essentially open, and it's not clear what the approaches you can take to interpret it. It seems like you have to like do it piecemeal and sort of design experiments. So I think one way that I like to describe it is that it seems like with a lot of big parameter models, where we're going towards is, so in biology, let's say, well, a neuroscientist, for example, when they want to try and design experiments to understand a part of the brain, they will design like a special purpose experiment to understand maybe the hypothalamus or the different parts of the brain, for example. And it seems like as we're approaching a lot of these 175 billion parameter models, it seems like that's the approach we also have to take. We might not necessarily say, oh, we're going to completely understand the entire 175 billion parameter model. We might just want to understand, has it learned gender? Has it learned, let's say, race? Has it learned to negate sentences? Has it learned to blah, blah, blah? And then what you can do in that case is design a specific experiment to figure out if it has learned gender or this or that. And then from that experiment, you can say, okay, yes, it has learned this thing. Yes, it hasn't. But the problem there is now everything you want to understand, you have to design a specific experiment to try and understand that. But that direction of designing a specific experiment to understand what a big parameter model is doing, that seems to be the direction that people are working on to understand those kinds of models. But it's completely unclear if this is going to be out. It's completely unclear what you can learn from this, because you don't necessarily know what GPT-3 is doing. So if you learn a model to like figure out what it's doing, you have to sort of, how do you know that what you learned is really the right thing? So there's a lot of challenges that remain. So, but I haven't seen, I will say actually, probably Sebastian will talk about this next week. The NLP community, they've actually been doing a lot of very interesting work on learning this kind of thing, because they have like special purpose data sets where you can try and figure out, maybe you have a parse tree, or you can figure out a specific property of a sentence you want to test in a model. So they're able to do a lot of these probing experiments where they're able to say, oh, the model learned this, it didn't learn this, it's doing this. And so there, it seems like you can design special purpose experiments to figure out what the model is doing. But a lot of these giant 175 billion parameter models, they're still trying to understand them is still completely open, in my opinion.
Thank you. Yeah. That's great, Julius. So another interesting question, I think this relates back to part of your answer, is around sort of the sanity of saliency, because you've actually been looking into that space. When we think about even this notion of how humans interpret things, or I would suppose animals interpret things, so you look at the general visual field and then you start to focus locally, iteratively, and then you can say it's a dog, it's a cat, just like you used that example. So this is a very interesting question that's asking, have you done a survey of humans to understand what it is that they're looking at when they think they're looking at that thing?
I see. Can you be more, so there's been some surveys of humans that's been done. I can talk about that. Can the person be a little more specific? Meaning, is the survey trying to decide what the human should rely on to figure out whether it's a dog, or should the survey be trying to figure out what the model is relying on? So is the survey trying to understand what the model is relying on, or what the human is relying on? That's my clarification.
So how about you go with the second part of that?
Okay, meaning what the human is relying on.
Yes.
Okay. Yeah, so so I haven't done those surveys. The kind of surveys that I've done are the ones where we train models and then we show people and we try and see if they understand what the model is doing, and if they better trust what the model is doing, and if what the model is relying on corresponds with what they think it should rely on. So, and the answer that we find is basically that it's unclear. So maybe so for example, I don't have a good example here, but I was going to show an example where the model is relying on the exact thing you would expect it to just for a particular image, but in a completely different image is relying on something else. And so essentially what we find is that the saliency maps that we show people, they're form of weak signals. When people actually have the outputs of the model, they rely more on that than the actual saliency map. So there's still more work that needs to be done on these saliency maps to figure out whether or not they're able to help a person actually debug a model. It's currently unclear. Some of the methods that's been, a lot of the papers that I've seen and some of the stuff that I've done are basically negative results. And so they show that the saliency maps haven't been helpful to people to actually use to debug models. But then there have been some other papers. So for example, integrated gradients, one of those methods, was tested with, I think, ophthalmologists to try and see if it better highlights part of the image that the ophthalmologist should pay more attention to. In that case, they were able to find that the ophthalmologist, it actually helped the ophthalmologist in diagnosing diabetic retinopathy. But in some of the other tests that I've seen and some of the ones that I've done, it hasn't been helpful. So it seemed like it might be context dependent, it might be task dependent as well. So I would say probably I've seen maybe 10 different papers where they've said it hasn't been helpful, and maybe 2 or 3 other papers where they've said it has been helpful. So it's still somewhat unclear, and this is part of the thing the field still needs to sort of try and work out, is when are these things useful and when are they not? So if I give you an explanation method, let's say this saliency maps or something else, when can I use it to debug a model? When can I use it to understand what a model is doing? And when can I not sort of expect it to help me understand? So that kind of when to use a tool and when not is still somewhat unclear. But this kind of thing is something people are starting to ask about. And I can, there's some interesting papers that have been published recently that I can send along after this as well.
Okay, thank you. Here's an interesting question. So Hospice would like to learn more about the open source explainability frameworks. And I think it's interesting, as you mentioned, Julius, there's been this Cambrian explosion of activation functions and optimization techniques and architectures and algorithms. And from what you suggested now, also there is a whole plethora, just by judging by the number of papers you showed year over year and just some examples you've used. So are these pretty much baked into the deep learning libraries like TensorFlow, PyTorch, Chainer, MXNet, or what does it take to bring these into sort of the real world, into production or deep learning programs?
They are essentially, so a lot of those tools are usually, they are built, let's say, with PyTorch or TensorFlow or whatever automatic differentiation tool you're using. But they're usually like a separate module. So it's like, you have to they're a separate package you have to import or use. So one of them can be, if the person that asks the question is paying attention, one of them can be Captum. It's from Facebook. That one is more focused on visualization methods. So in that package, you'll see, so it's in PyTorch, and you'll see a lot of, actually I think almost every method I described here, every visualization method I described here is there. So integrated gradients is there. The simple gradient method is there. Some other LRP-based input times gradients is there. So that Captain package has a lot of this methods implemented for PyTorch. Another one is called pair saliency. So if you Google PAIR saliency, you'll see a GitHub repo for, I think, TensorFlow, not TensorFlow 2.0, TensorFlow 1.0, where you can, a lot of these methods are implemented, and some other methods I didn't talk about as well. Another package that's very popular is called SHAP, for shapely values. And I actually didn't talk about shapely values at all, but you can use shapely values to also get feature importance and get feature maps. So SHAP is one, Lime is another one that is also very popular. So these are sort of the packages that I think are popular. There are probably a few other ones. The example methods that I talk about, there is not really a standard package, and it's mostly because some of those methods can be computationally expensive, but those ones you usually have to sort of implement your own from scratch. But they are not as widely used, even though they might actually be more useful in practice, but it's somewhat unclear. But I would say Captum, SHAP, Lime, there's another one called Torch Ray. Yeah, so these are ones that immediately come to mind. Pair saliency. So these are the ones that are sort of immediately come to mind.
Okay, interesting. Thank you. Let's do two more questions. This is an interesting question as well. So this is more of a practicality question, which is that it's great for somebody to say that we shouldn't use deep learning networks in high stakes decisions. But the reality is, when push comes to shove, unless there is some kind of law or unless there's some kind of explicit prohibition on the use of them, really, do you truly see this sort of uptake, or sort of in the launch of lots of new interpretable sorts of approaches that are just as high performing, technically speaking, as some of the DNNs?
I actually think you will. And part of it is that initially I was very, well, so I think you will, but this is a very unscientific opinion. I have no way to justify it. This is just my hunch and it's what I hope will happen. In terms of, I think you can still have a deep architecture that is designed to be interpretable from scratch. So there's a recent paper called Neural Additive Models. So those, they're not for computer vision, but they're designed for tabular data. So you can sort of train them on on a data that is in like a CSV or way the inputs are structured. So, but I think part of the difficulty is that training some of those models is actually more difficult than training a standard CNN. So with a standard CNN that you might want to train, you can just train it with stochastic gradient descent. You can usually just come up with a loss function and just optimize that loss function. With a lot of these more interpretable models, you might have to do like EM or do something more sort of more challenging optimization-wise, or even designing the architecture-wise. But I think, in my personal opinion, I think that's probably more and more, unless we figure out a way to sort of correctly debug models using post hoc explanations. I think that's the way, probably going to be the way to go, because you can, if you're working in a medical radiology data set, if you train a black box DNN, you can deploy it, because you have to really be able to make sure it's not relying on the scanner, it's not relying on all these potentially spurious correlations. And those things are actually very, very difficult to figure out ahead of time. And so if there's an easy way for you to sort of interact with the model or figure out a way how way the model is working, then it's better. And from my experience working with interpretable models versus the ones that are not in, the black box DNNs that are just millions of parameters, it's substantially easier to debug the interpretable models. So I think it's possible, and there's starting to be some work that are going in this direction. So Cynthia Rudin, actually, she has a paper on interpretable DNNs where you can combine the DNN pixel sort of image patch by image patch to create a model. And I think in cases where you really care about debugging your model, understanding what the model is doing, I think you will have to constrain the model from scratch. And I think it's just based on the current tools we have, it's easier to do that than to use a lot of post hoc methods. But it could be that maybe next year somebody comes up with a very good post hoc method that's able to that overcomes a lot of the challenges we have now. But that's my current sort of impression on where I'm leaning.
Great. So let's do one last question. This is, I think it really relates nicely to the question that you just answered. So, when we talk about interpretability, and based on what you just implied, it is very domain specific. It is very context sensitive. I mean, certainly in hospitals, it may be a very different set of rules. And even within the hospital, there may be many, many different sets of rules that apply in different conditions. So is there any research, or is there any kind of survey or some literature that looks at, maybe compiles an inventory of sort of situations, and then sort of the need for interpretability in those situations?
So there probably is, but I haven't seen sort of a paper that does a survey where they say its interpretability is required here, not for this task, or what kind is required, what kind is not required. So I haven't seen that kind of a survey. But I'm sure maybe there might be a survey paper that catalogs this. But I actually have a slightly different opinion on this. I think, so, I mean, it might not be what we call interpretability, but I think anytime you have to debug your model, basically try to figure out the mistakes that your model is making, try to figure out when it will make a mistake. And anytime it's very important for you to be able to debug your model, in my opinion, I think interpretability is very important in those cases. Even though, I mean, what you call interpretability might differ, but I think anytime you have to sort of really sort of understand why your model is making a mistake, make sure that your model is not making unreliable mistakes before you actually deploy it, then interpretability is very important. So that's my opinion.
Great. Thank you very much, Julius. This was a very thoughtful and thought-provoking presentation, and very happy that you were a part of this. And we hope that you'll come back in a couple of months to share some updates from your research and give us an updated lay of the land. So thank you very much on behalf of the Synthetic Intelligence Forum, and we hope you'll join us again very soon. Thank you.
Definitely. Thank you. Thank you. It was happy to present.